Hello friends, now we are seeing what is the potential due to a point charge. We already seen what is the definition of potential at a point in an electric field. It's the work required to bring a unit positive charge from infinity to the given point. Here we are finding what is the potential due to a point charge. Our aim is to find what is the potential due to this positive charge at a point P, which is at a distance r from our point charge or source charge. By definition, we have to calculate what is the work required to bring a unit positively test charge from infinity to the point P. That will be the potential at the point P. So to calculate that one, first we are finding what is the work required to move a small test charge, positive test charge Q0 from A to B. Suppose at this instant the charge Q0 is at point A. Q0 is a test charge. It is at a point A, which is at a distance x from the source charge. So it experiences an electrostatic repulsive force. Is it? What is that electrostatic repulsive force? We can write that electrostatic repulsive force F is equal to the electrostatics or Coulomb's force between them. F is equal to 1 by 4 pi epsilon 0 Q0 by distance square x square. This much repulsive force is experienced for Q0. So we have to apply some force which want to overcome this repulsive force. Then only we can move the charge from A to B. It should not be too large, otherwise it will be accelerated. Apply minimum this much force to move the charge from A to B. The distance between A and B is too small, that is dx. So first we are calculating what is the work required to move the charge from A to B through a small distance dx. Opposite direction of this electrostatic repulsive force. That we are writing the small work done is equal to dw is equal to the small work done dw is equal to that F dot dx. Work done is equal to F dot dx. Dx is a very small displacement from A to B. F is the minimum force required for to move. So the small work done is equal to F into dx into, see that the electrostatic repulsive force is in this direction and our displacement is just opposite direction. Angle between dx and f is what? 180 degrees. So we are writing f dx into cos 180. Cos 180 is minus 1. So we are getting this is minus f into dx. This much work is required to move the charge from A to B. But actually we want to bring the charge from infinity to the point P. So to calculate the total work, we have to integrate the small work done from infinity to the point R. That's it. We are taking to the point R. So from infinity to the point R. Let's see. The total work can be written as total work is equal to integral dw. Integral dw. That's equal to integral infinity to R minus f into dx. Minus f into dx. Okay. That's equal to total work is equal to take minus f here minus infinity to r minus is kept outside. Substitute the value of f is equal to 1 by 4 pi epsilon 0 q0 by x square into dx. X square into dx. Alright here. See here the work is equal to keeping all constant outside here 1 by 4 minus sign is there already minus 1 by 4 pi epsilon 0 q0 all are constant and infinity to r okay 1 by x square dx 1 by x square dx. Work is equal to 1 by 4 pi epsilon 0 q0 infinity to r 1 by x square dx. And the work is equal to keeping q0 upon 4 pi epsilon 0, and this is integral infinity to r x raised to minus 2 dx. What is that? Work is equal to q0 4 pi epsilon 0, what is integral infinity to r x raised to minus 2 dx is x raised to minus 2 plus 1 by minus 2 plus 1. You see, from a limit infinity to r. That is, work is equal to q0 4 pi epsilon 0, give the, okay, x raised to minus 2 plus 1 is what? X raised to minus 1. X raised to minus 1 is what? 1 by x. And 1 minus sign is there. So already we have a minus sign here. Minus and minus become plus. Okay. That is 1 by x infinity to r. So what's work done? Work done is equal to, we are rearranging this equation like this way. q0 4 pi epsilon 0 into upper limit 1 by r minus lower limit 1 by infinity. 1 by infinity is what? 0. So we getting the work is equal to, okay, rearrange this equation as 1 by 4 pi epsilon 0 q0 by r. This much work is required to bring q0 from infinity to the point P. We have to calculate what is the work required to bring a unit charge. This is work required to bring q0. So what's the work required to bring unit charge is known as potential. That is total work by magnitude of charge q0. It's equal to 1 by 4 pi epsilon 0 q by r. See, q by r. This is the potential at a point P. The potential at a point P is inversely proportional to the distance to the point. It means that potential to the very close to the charge is maximum, and we are moving away from the charge, potential is decreases, and at infinity potential becomes 0. Potential and distance to the point are inversely proportional. V is proportional to 1 by r. So if you are plotting a graph between V and R, it will be maximum to the near to the charge, and when R increases, what happen? Electrostatic potential is decreases and is 0 only at infinity. So now what you done is we calculated the electrostatic potential due to a point charge, and seen that potential due to a point charge is given by V is equal to 1 by 4 pi epsilon 0 q by r. It shows that V is inversely proportional to r. That is, very close to the charge, potential is maximum, and it decreases when you are moving away from the charge, and comes to 0 at infinity.